Hello students, we are now going to learn about vectors and scalars. What is a scalar quantity? Most of you might be knowing a physical quantity which has got only magnitude and no specific direction is called a scalar. Okay, for example, if mass of a girl is 43 kilograms, okay, what is the magnitude of this mass? Many of you might be thinking it is 43. But it's wrong. The whole thing is magnitude. Number and the associated unit together is called a magnitude. Okay? So magnitude alone gives you complete sense. I don't have to tell mass of the girl is 43 kilogram upwards or downwards or east or west. Direction is not required over here. It gives you complete sense. Okay? For example, there's another boy of mass say 50 kilogram. He can easily understand the girl's mass is 7 kilograms lesser than his mass. Okay? And suppose there's another girl whose mass is say 41 kilogram. That girl can easily make out mass of this girl is 2 kilograms more than the mass of this girl. Clear? So like that it gives you complete sense. So a physical quantity which gives you complete sense by magnitude alone, direction is not required. Such a physical quantity, we call it as a scalar quantity. Is that clear? For example, let us take density of mercury. Mercury symbol is Hg. Density of mercury is 13.6 into 10 power 3 kilogram per meter cube. I mean, a meter cube of mercury will have, this much mass. And this density doesn't have direction. This number and the associated unit together we call it magnitude. Okay? And that alone is enough to give us complete information about the density of mercury. So density of any physical quantity for that matter is a scalar quantity. Okay? What is the density of water? You all might be knowing density of water is 1000 kilogram per meter cube. Okay? And some physical quantities like relative density. What is relative density of a substance? You all might be knowing. Relative density is density of substance by density of water. Okay? So this is what you call it relative density. Let us try to find out relative density of mercury. This is density of mercury divided by density of water. This will cancel out and what is left out is just 13.6. Here we don't have unit, okay, just number is enough over here. So there are some physical quantities like relative density which don't have a unit, just number, that's enough. In fact, that is a scalar quantity and its magnitude is just number, it doesn't have a unit, okay. So for some physical quantities like relative density which do not have a unit, number alone will be magnitude. But whenever a physical quantity is having a unit like mass, it has got a unit over here. 43 kilogram. Kilogram is the SI unit of mass, Number and unit together will constitute magnitude. For relative density, the number alone is magnitude. For density, this is number, this is unit, together it is magnitude. Okay? So I think by this time it's very clear. Physical quantities which have a number and associated unit, number and unit together is magnitude. And for some physical quantities like relative density which do not have a unit, number alone will be magnitude. Okay? And scalars are those physical quantities where magnitude alone is enough to give you complete sense. Direction is not required. Okay? And what about vectors? Vectors are physical quantities which have not only magnitude and direction but they also obey the laws of vectors. Okay? So physical quantities which have magnitude alone are scalars and physical quantities which have magnitude, direction as well they obey certain laws of vectors and those quantities we call them as vectors. Okay? So physical quantities which have magnitude, direction and which obey the laws of vectors are vector quantities. What are laws of vectors we are going to learn as we proceed in the topic. Okay? Let me give a beautiful example of vector quantity. Suppose a group of new students land up in Hyderabad and they are at this point P. And suppose they want to go to some science center which is somewhere over here. Say it's about 10 kilometers from point P in this direction. If we consider this as east and this as north, suppose this is towards northeast. From this point it's towards northeast in that direction, northeast. But then this group of students is very new to the city and they just want to reach the science center. Okay? And they're inquiring about it. Suppose they happen to meet one person A and they ask this person, please can you give us the address of science center, where is it like? That person says, I don't know. Well, that person definitely is of not any help to this group, right? Suppose another person B, they inquire with this fellow, okay, how far and where is the science center? And he says, oh, it's 10 kilometers away from here. But he doesn't know exact direction, but he knows it's 10 kilometers away from this point P. Okay, to some extent he is helping you, but he's not helping you completely because he's giving you number and magnitude. He's giving number and unit. That means he's specifying the magnitude, but is not giving you the direction. So, by this magnitude alone, can you reach science center? Obviously, yes, but with lot of difficulty. You can use your common sense. 10 kilometers from point P could be anywhere on the surface of a sphere of radius 10 kilometers. Imagine a big football. Okay, I'm drawing here in 2D. I can't draw 3D on the board being a plane. So imagine these people are at the center of this football at point P. Imaginary football of radius 10 kilometers. Every point on the surface of the football is 10 kilometers away. But using your common sense, this science center is not hanging up in air, 10 kilometers up in air. So it's on the surface 10 kilometers away. So don't have to worry about 3 dimensions. You can search the science center in 2D. But then the possibility how to get there, if you just know magnitude and don't know anything about the direction, the thing is you need to travel 10 kilometers from here, point P, and then you need to travel in the circumference of a circle whose radius is 10 kilometers. Somewhere on the circumference you will end up at the science center, and it depends how quickly you will be able to get there. Okay? But it's not a very nice way to reach the science center. Fine? But suppose another person C comes along and you inquire with that person, where is the science center? And he tells you, yes, I can help you. It is 10 kilometers from here and it is northeast. That means from point P, you need to, this person is helping you. The magnitude is given, direction is given to you. You just need to, this is the position, this is east, this is north, exactly 45-degree angle with east, and of course another 45 degree with north, because northeast means it is exactly between north and east. So if you need to turn in that direction, walk straight 10 kilometers, you will end up at the science center. Is it clear? So direction is equally significant over here. This particular quantity 10 kilometers northeast in fact is displacement of this group of persons or group of students in traveling from point P to S. This is a displacement. Displacement's another name is change in position. So this change in position vector or displacement is a vector quantity because along with magnitude means number in unit, direction is equally significant. Okay, you can also consider another example. Suppose this is a one-way street. Traffic is allowed to travel only from say A to B in this direction. But if somebody is driving a bike in opposite direction this way, traffic police will hold that person irrespective of whatever velocity he is driving at. Even if he is driving at a moderate speed, say normal 40 km/h, even then the traffic police will challenge this fellow not for the magnitude of velocity which is 40 km/h, which might be under normal limit, okay, but they challenge him for the wrong direction, because on this one-way street, suppose The traffic is allowed to move only from A to B. He is driving the other way. So direction is equally significant. The traffic police is not interested in magnitude of your velocity, is also not only interested in magnitude of velocity but also in direction. Okay, so direction is equally significant. He is interested in your velocity and not your speed. You know, the speed with direction is called velocity. More about that you have already learned. More about that in kinematics. Okay, let me give some examples of scalars and vector quantities. Mass, time, speed, distance are scalar quantities. In fact, this is a group of scalars and this is a group of few vector quantities I have placed over here. Lot more scalar quantities you will come across when you reach higher classes. In fact, most of these quantities I am just classifying them as scalars and vectors. I am not going to explain what they are in detail, which you are anyhow going to learn in your higher classes or in subsequent chapters. Okay, so electric potential, in fact you will also come across magnetic potential and gravitational potential. This potential is a scalar quantity, work is a scalar quantity, power is a scalar quantity, energy could be kinetic energy, potential energy or heat energy, sound energy, light energy, any form of energy is scalar. Volume is a scalar quantity. Density of any quantity, you know, density of gold is 19.3 gram per centimeter cube, mercury 13.6 gram per centimeter cube, water 1 gram per cc. Or density of any quantity for that matter is scalar. Pressure is scalar quantity. Charge, electric charge is scalar quantity. Temperature is a scalar quantity. Electric current is a scalar quantity. Velocity of light is scalar quantity. Here you might be a bit confused because here velocity I have included in vectors, but velocity of light I am calling it scalar. It is better to call it speed of light, but most of the books do print it as velocity of light. That's the reason I have written over here velocity of light, but it is better to call it speed of light and it is a scalar quantity. Okay, if I ask your velocity or my velocity or velocity of a car, that is a vector quantity, but velocity of light is a scalar quantity. It is better to call speed of light. Please remember it. You will learn about it in detail in your higher classes. Okay, specific heat is a scalar quantity and even finite angle. When I say finite angle, I mean say 90 degree, 30 degree, 40 degree, 100 degree, 2000 degree or 360 degree. That finite angle is a scalar quantity. Okay, coming to few examples of vectors. Displacement is vector. Area is also regarded as a type of vector. More about what type of vector it is we'll learn in higher classes. Velocity, acceleration is a vector. Remember, when I say acceleration is a vector, it could be acceleration due to gravity or acceleration due to any other force is a vector. Force is vector, momentum is vector, impulse is vector, very small angle is a vector quantity. Remember, here I told finite angle or a big angle like 30 degree, 40 degree, 90 degree is a scalar quantity, whereas very small angle, negligibly small angle, that is in fact I am including in vectors. It's a vector quantity. Why this is vector and why this scalar, definitely you will learn in higher classes. As of now, I am just classifying. Okay, angular velocity is a vector quantity, angular acceleration is a vector quantity. What is angular velocity? What is angular acceleration? Again in higher classes. Intensity of electric field. Similarly, you have in physical quantity called intensity of magnetic field and intensity of gravitational field. All these intensities of fields are vector quantities. Okay, more such quantities you will encounter as you proceed in higher classes. Okay, mind you, scalar quantities can be both positive as well as negative. For example, electric charge is a scalar. You can have a positive charge as well as negative charge. In fact, in cold countries you might be knowing temperature goes below 0 degrees Celsius. It could be minus 20 degrees Celsius outside. Okay, so it's below 0 degrees Celsius means it's negative. It's a scalar quantity. It can be positive or negative temperature. Even work done by force, as we are going to learn in chapter work power energy, work done by a force can be positive as well as negative, even though work is a scalar quantity. So scalars can be both positive as well as negative. Is it clear? Next, representation of a vector. How a vector is represented. For example, vector A is a 100 Newton force towards northeast. This is magnitude, number and unit, and this is direction. Okay, so what we do is we take some convenient scale, say 10 Newton equal to 1 centimeter. Now this vector is represented by a straight line segment. Length of the line drawn to some scale will give you magnitude. This is a vector A, which is 100 Newton northeast. This magnitude and this is direction. So this is called tail of the vector. Let me call it P as tail and Q as head of the vector. So this vector PQ is nothing but vector A. See, we are taking a scale conveniently, say 10 Newton equal to 1 centimeter. So 100 Newton means, you know, for every 10 Newton you are going to draw a line 1 centimeter long like this. So for 100 Newton you need to take a line 10 centimeter long and arrowhead will indicate the direction. Okay, so a vector is represented by a straight line segment. Length drawn to some convenient scale will give you magnitude and arrowhead indicates the direction. Okay, this is called head of the vector and this is called tail of the vector A. Is it clear? Fine. See, remember, for 10 Newton it is 1 centimeter. So 10 times 10 Newton we need. This is going to be 100 Newton. Alright. So 10 times 10 Newton. This 10 Newton we are representing by 1 centimeter. So 10 times 1 centimeter is going to be 10 centimeter long line. Fine. Like this 10 centimeter long line. And this is the direction. Fine. You know, this is northeast, directed towards northeast. According to this figure, see, this is the direction northeast, 45 degree with east, 45 with north, northeast. So this is the direction. Arrow indicates direction. Okay, you should not draw this line segment in this direction or in that direction. You need to go by some reference. This is the east and this is north, suppose. So northeast should be in that direction, and length should be 10 centimeter. This is the head of the vector. This is the tail of the vector. Clear? Let us consider another vector. Say velocity is again a vector quantity. Say velocity of a car is say 50 meter per second towards east. How to represent it? Some convenient scale again. Let us take 10 meter per second equal to 1 centimeter scale. So now this 50 meter per second is going to be 5 times 10 meter per second. This is, we are calling at 1 centimeter. So this will be 5 into 1 centimeter, a 5 centimeter long line, and direction should be towards east because this is magnitude and this is the direction of velocity of a car. So velocity of this car is, you know, 5 centimeter long line here, and this direction is towards east. Fine. So it is represented by this, let me call it P again Q. This is the velocity vector. Length of the line should be 5 centimeters. Direction is like this. This is head of the vector, this is tail of the vector. Clear? Fine. You can take any convenient scale. For example, a force acting on a particle is say 20 Newton towards south. This is magnitude, this is direction. How to represent it? Some convenient scale. Let us take 1 Newton equal to 1 centimeter. Now 20 Newton means you need to draw a line 20 centimeter long because every Newton will be 1 centimeter now according to the chosen scale. Fine. So but this is north and this is south. So you need to draw southward, downward. So this line, okay, if I call it some PQ again. So this is the vector or force F. Length should be 20 centimeter because 1 Newton is 1 centimeter. 20 Newton, 20 centimeter long line towards south, downwards, I mean over here with reference to this figure, this is south, so downwards. This is head of the vector, this is the tail of the vector. Fine. This is how vectors are represented by straight line segments. Length of the line drawn to some scale will give you magnitude. Arrowhead indicates direction. Is that fine? Let us see the print notation. Some of the books will print a bold letter like this. You all know very well force is a vector. Suppose force is 60 Newton towards east. This is magnitude and this is direction. So some books will print it like this. Bold letter means it's a vector. Just, you know, thin letter means it's just magnitude. Fine. Some other books will follow a different notation like this. Over here. You know, this letter symbol, letter with arrowhead is vector, magnitude as well as direction. And just letter without arrowhead is magnitude. Fine. Some other books will follow a different notation altogether again. See over here, as usual, a letter with arrowheaded vector, magnitude as well as direction, and mod of that, okay, mod of that is just magnitude. You know, this mod f is read as magnitude of vector f. Okay, mod a is read as magnitude of vector a. Okay, you all know very well mod is always positive, so magnitude of a vector is always positive. Okay, we have studied in algebra mod x is x if x is positive and mod x is minus x if x is negative, because x is negative means negative will become positive because mod is always positive. So magnitude of vector a is always positive. Mind you, mod a is read as magnitude of vector a. Okay, some books bold letter magnitude and direction vector, a thin letter just magnitude. Fine. A letter with arrowhead vector, both magnitude and direction. Letter without arrowhead, just magnitude. Letter with arrowhead, magnitude and direction. Mod of that is magnitude. Fine. So these three notations are used in print. Anyone you can easily make out once you know the notation. Clear? Let's now discuss briefly about types of vectors. Concurrent vectors means vectors acting at the same point. Like if all the vectors are acting at the same point, then they are known as concurrent vectors. Like, okay, vectors A, B, C and D shown over here are acting at this point, at the same point, so they are concurrent. Okay, let's now discuss about coplanar vectors. As the name itself signifies, vectors lying in the same plane are known as coplanar. Like for example, if a vector A is in this plane of the board and B is also in the plane of the same plane, I mean in the plane of the board, then these two vectors are coplanar. Fine. Next, collinear vectors. As again the name is very much clear, collinear means vectors acting along the same line. Okay, they need not be in the same direction, they could be in the same direction or opposite direction, they will be acting along the same line. Vectors acting along same line are collinear. Here ABC are collinear vectors. Fine. Now what about like vectors? Like vectors means vectors acting in the same direction. Like vectors are also known as parallel vectors or co-directional vectors. Co-directional means same direction. Fine. Co-directional. So like vectors, parallel vectors or co-directional vectors, they will be acting in the same direction. Fine. In this case, vector A and vector B are co-directional. They are acting in the same direction. When they are acting in the same direction, obviously angle between those vectors is going to be 0 degree. Fine. So angle between like vectors or parallel vectors or co-directional vectors is 0 degree. Mind you, all these three names refer to the same type of vectors. Co-directional, like or parallel vectors means vectors in the same direction. Now if they are in opposite direction, fine, you just call them unlike vectors or anti-parallel vectors. Unlike vectors, or this will not be parallel vectors, they will be anti-parallel vectors. Fine, they will be anti-parallel vectors and you don't call them co-directional. Fine. Unlike vectors or anti-parallel vectors, vectors acting in opposite direction, and when these two vectors are in opposite direction, like one is towards east suppose, then the other vector is going to be towards west, and obviously the angle between those two vectors is going to be 180 degree. Fine. So angle between unlike vectors or anti-parallel vectors is 180 degree. Fine. And when do you say the two vectors are equal? Obviously they should have same magnitude and same direction. Mind you, magnitude means number and associated unit. Magnitude and direction, if both are same, then you say the two vectors are equal. For example, vector A is a force 10 Newton towards northeast. This is direction, this is magnitude. Then another vector B, which is also having the same magnitude of 10 Newton and also same direction as northeast, then these two vectors are said to be equal to each other. Mind you, even if direction is different or magnitude is different or both magnitude and direction are different, then the two vectors won't be equal to each other. Fine. So for two vectors to be equal to each other, they should have same magnitude and same direction. Fine. only then you can say the two vectors are equal to each other. Fine? Is it clear? For example, if a car is moving with a velocity of 10 meter per second towards east, car A, another car is moving with a velocity, car B, with 10 meter per second only, but the direction is towards north. Are these velocities equal? No. Even though they have the same magnitude of 10 meter per second each, the directions are different. This direction is towards east and this one is moving towards north. So their velocities are not equal. You cannot say VA is equal to VB. In fact, VA is not equal to VB. Even though they have same magnitude, they are not moving in the same direction. Fine? So these two vectors are not equal to each other. And now let this car is moving with 20 meter per second towards east. And this car B is also moving towards east, but with just 10 meter per second. Are these velocities equal? Obviously no, because now magnitudes are different. Even though directions are same, magnitudes are different. Even now velocity of car A and car B are not equal to each other. Is it clear? And obviously when the magnitudes are different and directions are also different, magnitudes are different, directions are also different, definitely even now they are not equal to each other. For two vectors to be equal to each other, they should have same magnitude and same direction. Is it clear? In case of vectors, as you know, arrowhead indicates direction. Suppose this is a vector A, say 10 Newton force towards east. This is magnitude and this is direction towards east with reference to this east and north system. In fact, if I take this direction as positive, any convenient direction can be chosen as positive. If I take eastward direction as positive, this direction, any vector in this direction will be positive. Whether it is a velocity vector or force vector or a momentum vector, any vector towards east will become positive, and then any vector towards west will become negative, right? So any vector in opposite direction will become negative. If this is a vector B, if I call this as 10 Newton, I am taking eastward direction positive, then B would become, say, is 6 Newton, so it will become minus 6 Newton. Minus sign indicates it's in opposite direction. Fine? Is it clear? So if a particular direction is taken as positive for vectors, then opposite direction becomes negative. Fine? If I conveniently choose this particular direction as positive, any vector in this direction should be taken as positive and any vector in opposite direction should be taken as negative. Fine? Now let us discuss about a vector and a negative vector of that vector. For example, suppose now vector A is once again 10 Newton magnitude, but it's in northeast direction. Magnitude, direction, according to this, northeast means 45 degree with east, 45 degree with north. So this is vector A, suppose. Now if you consider another vector which is having same magnitude as that of A, say magnitude of this vector B is also 10 Newton, but it's not towards northeast, rather it is towards southwest, exactly opposite to northeast, exactly opposite to northeast, opposite to north, south, opposite to east, west. So opposite to northeast will be southwest. So this direction, southwest direction, this is west and this is southward, this is southwest, northeast, southwest. Fine. So this vector B and vector A, they do have the same magnitude of 10 Newton each, but their directions are opposite. Such vectors are known as negative vectors of each other. So vector A can be written as minus B, or vector B can be written as minus A. Okay? So two vectors are said to be negative vectors of each other if they have same magnitude and opposite direction. Mind you, when I am telling same magnitude, I mean same number and same unit as well. Fine? A vector and a negative vector should have same number and same unit, just that they do have opposite direction. Fine? Null vector is a vector with zero magnitude and no direction or no specific direction or insignificant direction. Okay, as you know, for example, say force is 0 Newton. How do you represent this force A, which is 0 Newton? For example, if the force would have been like this, say 10 Newton or something like this towards east or in any direction, this length of the line drawn to some scale will give you magnitude. Fine. But now as I am telling you, this particular force A or vector A is of 0 Newton, 0 magnitude, means no length. This tail If I call this tail as P and this is head as Q, this tail end, it becomes smaller and tail and head dwindle into a point. So it's just represented by a point. Mathematically, null vector is represented by a point. Length becomes 0 because we know length drawn to some scale will give you magnitude. Here magnitude being 0, okay, it's almost point, and when it is a point, head and tail are coincident, so you can't associate a specific direction to it. Fine. So there is no meaning to the direction of a null vector, even though its magnitude is 0. We don't say it has no magnitude, we say its magnitude is 0 and it has no specific direction, or its direction is meaningless. Fine. Something we call it as a null vector. More about this you will understand in different chapters like kinematics and in higher classes. Fine. So null vector is a vector with 0 magnitude and indeterminate or meaningless direction. Okay, or direction of a null vector has no meaning. Fine. Suppose a force of 10 Newton towards east is acting on this body at this point, this magnitude, this direction. Now if another force of equal magnitude, equal length, but in opposite direction, force B is acting towards west in this direction, this is east, this is towards west, this magnitude direction. And if I need to add these two vectors, as you might be knowing, these two forces are pushing this particular body with equal and opposite force. They are in opposite direction. They just cancel out and the result is going to be a null vector. Result is going to be 0 Newton. This is how we give meaning to a null vector. Fine. When two or more vectors they cancel out, you get a null vector. Fine. But it does have a unit, because we have learned in units and dimension chapter different physical quantities, when they are separated by plus sign, equality sign or minus sign, they should have same unit. Okay, so here unit of vector A Newton, unit of vector B Newton, unit of this result should be Newton. Even if it is 0, it should be Newton. So null vector has a unit. Fine. Velocity is a vector, and velocity, when it becomes null vector, its unit will still remain meter per second. It will become 0 meter per second. Okay. And acceleration is a vector, unit of acceleration is meter per second square. When it becomes a null vector, acceleration becomes 0 meter per second square. So null vector has a unit. Fine. Null vector of force, unit will be Newton. Null vector of velocity, unit will be meter per second. Null vector of acceleration, unit will be meter per second square. But null vector's direction is meaningless because it is a point. Fine. Mathematically it is represented by a point. Fine. Let us consider a vector A which is 10 Newton towards northeast, with reference to that figure northeast. And what we'll do is, we'll just take this vector A which is 10 Newton towards northeast, magnitude and direction, and we'll divide this vector by its own magnitude, means mod A. Mod A is magnitude of vector A. Fine. We're dividing vector A by its own magnitude. See, this is vector A divided by its magnitude. Magnitude mod A is what? 10 Newton. Mind you, number and associated unit. Number and unit together is magnitude. Mod A is 10 Newton. This is direction. Now when you do this, what is happening is Newton cancels out, 10 cancels out. What is left out is just 1 towards northeast. Mind you, only direction is remaining, which is same as the direction of vector A. Vector A is 10 Newton towards northeast. What I am getting now is just number 1 in northeast direction. Just number 1. A length 1 unit along northeast without any unit. Remember, Newton is also getting cancelled here. This particular thing is called unit vector of vector A. We denote it by A cap. Fine. So we denote it by something like A cap. Okay. Something like this, A cap. Unit vector of vector A. Unit vector of vector A, or unit vector in the direction of A, or unit vector along A, whatever you want you can call it. It is nothing but it is number 1 in the direction of A. Just 1 in the direction of A. Mind you, this is nothing but unit vector of vector A and unit vector of vector A. Okay? It has no unit. It is just number 1. Just number 1 in the direction of A. It has no unit. Unit vector has no unit. It is just used to indicate the direction. Okay? So unit vector of vector A means it's number 1 in the direction of A. Unit vector upwards means number 1 up. Unit vector down means number 1 down. Unit vector towards east means 1 towards east. So unit vector is just used to indicate direction. It has no unit. Fine? Unit vector is unitless. Suppose you have a velocity of a car which is 20 meter per second towards east. Magnitude, direction towards east. Now what will be the unit vector of velocity of this particular car? That will be velocity of the car divided by mod of this. A by mod A, V by mod V. What is velocity? You all know 20 meter per second towards east. But when it comes to unit vector, you don't worry about magnitude because you need to divide by mod V. Mod V is 20 meter per second and that easily gets cancelled out here and you have just direction, that will be 1 towards east. So number 1 towards east, just 1 towards east, direction indicated. Fine. So unit vector of this velocity will be 1 east because that velocity is towards east. Fine. Unit vector has no unit because unit is getting cancelled. V by mod V is unit vector of V. Fine. And when do you think a vector changes? Obviously a vector changes if there is a change in its magnitude or direction or both. For example, suppose you are driving a car towards east with a velocity of 10 meter per second. Magnitude is 10 meter per second, direction is east. Fine. You are not changing the direction, but you are accelerating in the same direction. Fine. And velocity is no longer 10, magnitude is no longer 10 meter per second, rather it becomes say 12 meter per second. You are still moving in the same direction. Even then velocity has changed because magnitude has changed. Fine. Here velocity is changing because there is a change in its magnitude. Sometimes you may move with the same magnitude, same speed, but instead of going towards east, you are turning. Even if direction is changing, velocity is changing. Instead of east, now you are moving towards north, suppose. You are turning towards north and moving towards north with the same magnitude, but different direction. Even then velocity changes. Fine. And obviously, when you change both magnitude and direction, even then it changes. Say magnitude becomes 20 in direction instead of north, now it becomes east, or instead of east it is north, even then velocity changes. A vector changes if there is a change either in magnitude or direction or both. If there is no change in magnitude and no change in direction, then vector doesn't change. Clear? If neither magnitude nor direction changes, vector doesn't change. Vector changes if there is a change either in magnitude or direction or both. Fine? Suppose vector A 10 Newton northeast is acting at point P on this body. And now what I am doing is, I'll just slide it parallel to itself. I'll move it parallel to itself so that it's no longer acting at point P, rather it is acting at point Q on the same body. It is acting at a different point, but once again it is in the same direction. Its magnitude is once again 10 Newton and it is still towards northeast. See, same magnitudes, direction is also same. The only thing is, earlier it was acting at point P, now it is acting at point Q. So here what we are doing is, we are changing the point of application of vector. We are just changing the point of application of vector without changing its magnitude or direction. Fine? We are neither changing direction nor changing its magnitude, but we are changing the point of application. Earlier it was acting at point P, now it is acting at Q. You all know very well, vector changes if there is a change in its magnitude or direction or both. Am I changing here magnitude? No. Am I changing the direction of the vector? No. If there is no change in its magnitude or direction, vector doesn't change. Here vector doesn't change. But here we are changing the point of application of vector. Earlier it was acting at point P, now it is acting at point Q. So we are just parallelly shifting the vector to itself. We are sliding the vector parallel to itself without changing its magnitude and direction. And this process is called translation of a vector. Okay? What we call it? Translation of a vector. That means changing the point of application of a vector without changing its magnitude or direction is called translation of a vector. Vector doesn't change due to translation. Vector doesn't change due to translation. Okay? So I am just shifting the vector, sliding the vector parallel to itself. Vector doesn't change. It is called translation of a vector. Changing the point of application of a vector without changing its magnitude and direction is called translation. and vector doesn't change due to translation. Is that clear? As you might remember, we defined vectors are physical quantities which have magnitude, direction and obey the laws of vectors. Let us study few laws of vectors. Vectors do not obey the ordinary rules of algebra. They have a separate algebra called vector algebra. Few basic things about it, like addition of one vector with another vector, subtraction of one vector from another vector. These things we are going to learn now. Okay? Vector algebra in detail you are going to learn in higher classes in mathematics. Okay? Suppose you take 3 minutes to eat your food and another 4 minutes to dress up. Put together time is always going to be 7 minutes. That means 3 minutes plus 4 minutes is always going to be 7 minutes. Time is a scalar. It will obey the ordinary rules of algebra, ordinary addition, whatever we have learned in our basic classes. Okay? And moreover, you might have studied in indices chapter, or you might have studied in chapter squares and cubes. A plus b whole squared is going to be a squared plus b squared plus 2ab in case of scalars, which is not necessarily true in case of vectors. 3 plus 4 need not be always equal to 7. Moreover, a plus b whole squared need not be always equal to this. That means these ordinary rules of algebra are not obeyed by vectors. Let us see what type of algebra vectors do obey. Suppose you are here, in your residence at point O, and suppose you travel 3 meters towards east. 3 meters towards east displacement to reach point A. Then you turn towards north and travel 4 meters towards north. How far are you from your residence? Okay, 3 meter east plus 4 meter north. Can you say now 3 meter east plus 4 meter north, is it equal to 7 meters? Obviously it is not 7 meters, because see, initially you at this position, you traveled this much and then this much. How far are you from your residence means it is this. Okay, so this is your displacement, and you all know very well, using Pythagoras theorem, you can say that OB, displacement OB is nothing but under root this squared plus this squared. That means root over 9 plus 16, that is root 25, is going to be 5 meters in this direction. And how to get that direction? You know, this is eastwards according to that reference. So this 5 meters, is making an angle, tan theta. In simple trigonometry, you might have learned that tan theta is going to be opposite by adjacent, here 4 by 3. So tan theta is 4 by 3. It means theta can be written as tan inverse. Theta is tan inverse 4 by 3. So at this particular angle, okay, the displacement is at this particular angle north side of east. This is east, this is north side of east. See, east, north side of east. So how do you write 3 meter east plus 4 meter north is equal to 5 meter at an angle theta equal to tan inverse 4 by 3. You see, tan theta is 4 by 3 means theta is tan inverse 4 by 3. Tan inverse 4 by 3. Let me write this in a small bracket over here. Tan inverse 4 by 3. Okay, north side of east. Okay, north side of east. Something like this. So this becomes magnitude and this becomes direction of this vector. 3 plus 4 is here 5 meters. It is not necessarily 7 meters. Of course, it can as well be 7 meters. For example, Suppose you are here at point some say P, you're traveling 3 meters towards east, and then again you are traveling 4 meters towards east. East only. In both cases you are traveling towards east only. Now as your common sense might be telling, this is your initial position, this is your final position, and how far are you from your residence means all this much far. Fine? All the way from here till here, and it's obviously 3 plus 4. In this case it is going to be 7 meters. 3 meters east plus 4 meter east is going to be 7 meters towards east. So in this case 3 meters plus 4 meters is 7 meter. So it not only depends on magnitudes of this individual displacements but also on their directions. If both these displacements are in same direction, then the resultant is going to be maximum, and in that case it is going to be 3 plus 4 equal to 7 meters. But when this 3 meter and 4 meter are mutually perpendicular, like this is towards east and this is towards north, then result is not 7. 3 east plus 4 north is 5 meters. 5 meters at an angle. Tan theta is 4 by 3 means theta is tan inverse 4 by 3 north side of east, something like this. So 3 plus 4 could be 7 meters, or it could be even less than that, much less than that. Let us see how it can be less than that. Scalars don't do this. You know scalars, 3 plus 4 is always going to be 7. Time is a scalar quantity. 3 minutes plus 4 minutes is always going to be 7 minutes. Fine. For example, you are at your residence at point O. Now you travel say 3 meters towards east. You undergo this displacement. Then you turn back and you travel towards west, and that you have done say 4 meters. Now actually you're moving along the same line, but only to show I am showing it line a bit displaced. You're moving along and then coming back. You're moving 3 meters and then you're coming back along the same line. But to see it clearly, I am showing the red colored line a bit displaced, and this is 4 meters suppose. So how far are you from your house? Your house is at this point O. You travel 3 meters east and then turn back to travel 4 meters west. So what is your displacement? Obviously this is your initial position, this is your final position. You are just 1 meter away from your house, and that is towards west. That means I can safely write now like this: 3 meter east plus 4 meter west is 1 meter west. The simple reason why I am able to do this is, I told you very clearly, if two vectors are in opposite direction, one direction we can take positive means opposite direction becomes negative. That means I want to add this 3 east and 4 west. 3 east and 4 west. I can safely write this east direction as minus west direction. Because east and west being opposite to each other, east can be written as minus west, and then I have minus 3 meter west plus 4 meter west becomes 1 meter west. So that's going to be the value. Let me bring it back and write 3 meter east over here. So 3 east plus 4 west becomes 1 west. So when two vectors are in opposite direction, the result's magnitude will be equal to the difference of their magnitude. In this case it is 4 minus 3, which is 1, and the direction of the resultant will be the direction of the larger vector. In this case, a smaller one is 3 meter towards east and larger one is 4 meter towards west. This vector has got greater magnitude. So when two vectors of opposite direction are added to each other, the result will be equal to the difference. Magnitude of result will be the difference of the two vectors, which is in this case 4 minus 3 meters is 1 meter, this magnitude, and direction will be the same as that of the larger vector. Fine. And of course, when two vectors in the same direction are added up, the magnitude of resultant will be same as the sum of their magnitudes, that is 3 plus 4 is 7, and direction obviously same as that of any one of the vectors. Fine. So this way 3 plus 4 could be 1, 3 plus 4 could be 7, 3 plus 4 could be 5. If the angle is 90 degree over here, the 3 plus 4 becomes 5. If the angle is 0 degree, 3 plus 4 is 7. And if the angle is 180 degree, when they are in opposite direction, angle is 180 degree, they are anti-parallel vectors. Over here 3 plus 4 becomes 1, For any other angle, you can have a different value of the vector resultant. Fine. In fact, resultant will be maximum for given two vectors when they are in the same direction, and minimum when they are in the opposite direction. For any other angle, resultant lies between this minimum and the maximum value. When individual vectors are 3 meter and 4 meter, then their maximum value is 7 when they are in the same direction. The minimum value is 1 meter when they are in opposite direction, and that means when angle is 180 degree. For any other angle between 0 to 180, any other angle between 0 to 180 degree, the resultant also lies between 1 to 7. How to get that resultant's value, you're going to learn in your higher classes. As of now, just remember that 3 plus 4 is not necessarily 7 in case of vectors. Okay, it could be anything depending on the angle. Of course, that anything should lie between 1 meter and 7 meters magnitude I'm talking about. See, for example, if you travel say 3 meters this way and 4 meters this way. So how far are you from your house? Obviously 3 meter in this direction plus 4 meter in this direction could be something like this. This is the effect. You are here, finally you are here. This is your initial position, this is your final position. So if I call this vector A and this vector as B, how far? Okay, 3 east plus 4 in this direction. How far are you from your house? This far. So this becomes the effect or resultant. Okay, something like this. So it could have any value between 1 and 7 depending on the angle. Is it clear? Now you have a brief idea about how vectors get added up. Let us now study something called triangle law of vector addition. Let me give the statement first, then I'll explain. The statement is something like this. If two vectors can be represented by two sides of a triangle in order, then closing side of the triangle in reverse order gives the resultant in both magnitude and direction. For example, if OA is a vector A and AB is vector B, then the closing side, this side of the triangle in reverse order gives the resultant in both magnitude and direction. Remember, we are telling closing side in reverse order. That means if two vectors can be represented as two sides of a triangle in order, like tail head, then again don't tell tail head, tell tail head, tail, because we want third side in the reverse order. Fine. So this is vector A, this is vector B, then the small b, the resultant is going to be this. This is the resultant of vectors A and B. I mean OA plus AB is going to be OB. I mean tail of the first vector, tail of the resultant, head of the last vector, head of the resultant. See, tail of the first vector, tail of the resultant, head of the last vector, head of the resultant. I mean head of the second vector, head of the resultant. Tail, head, tail. Fine. So remember, that's the reason we are telling third side in reverse order. Okay. When I am telling two vectors can be represented by two sides of a triangle in order, when I say in order, what I mean is second vector should start where first vector ends. I mean tail of the second vector is on head of the first vector. See, tail head. Again don't tell tail head, because result is not in order. Result is third side in reverse order. Tail head, head tail. Fine. That's what we mean when we say closing side in reverse order. Tail head tail. It's so easy to understand, in fact. Okay, triangle is so easy to understand. Suppose this is your residence, you are here right now, and you undergo displacement this much, A, to reach here. Then you traveled in this direction to reach point B. How far are you from your house? This much. This far. This displacement 1 plus displacement 2 will be this displacement. Tail head tail. You travel this much, you travel this much. How far are you? This far. So don't you think effect of this A and B put together is this R? So instead of A and B having a separate displacement like this, instead of having separate displacements of A and B, you can directly have A plus B displacement in this direction, this much. Fine? Is it clear? And obviously in any triangle you might be knowing sum of any two sides will be more than the third side. So if you individually try to add up the magnitudes of this A and B, definitely they will be greater than the magnitude of this R. Fine? What I mean is mod A plus mod B in this particular case as the figure is represented on the board has to be more than mod r. Okay, remember mod r is nothing but mod a plus b, because r is resultant of a and b. So for r I can write down a plus b. Fine. So something like this. Any triangle you can say this is magnitude of this, side of the mod a is nothing but length of this vector, mod b is length of this vector, mod a plus b is length of this side. Fine. So sum of two sides is more than the third side in any triangle. So whereas in scalars 3 plus 4 is always 7, over here it's not necessary. Fine. Tail, head, tail, this is the resultant. Fine. As an extension of triangle, let's try to understand something else. Suppose you are at point O and you undergo displacement vector A to reach point capital A, and from here A to point B undergoing a displacement of small b. Suppose then you return back along this path back to point O. Okay. Then suppose you return back from point B back to point O over here, and let this displacement be called as C. Fine. Initially you are at this point, you travel this much to reach point A, then this much to reach point B, then you return back all the way to reach point O again, to your residence, back to your home. How far are you from your residence? Obviously 0. You are at your residence, travel this much, travel this much, travel this much back to home. How far are you from your home? 0. That means A plus B plus C now is going to be 0. Okay, or null vector I should say. See, tail, head, tail, head, tail, head, close figure. So result is going to be 0. Remember, C is not the resultant now. C is not the resultant of A and B, because we know according to triangle law, resultant is third side in reverse order. Let us try to add up A and B to get what A and B actually is over here. See, tail, head, tail, head. Now resultant will be head, tail, third side in reverse order. This will be the resultant. This will be the resultant of A and B. Okay, see, tail, head, tail, third side in reverse order. This is the resultant. Tail, head, tail. That means if you travel this much and this much, you will be how far from your residence? This far. But now again you are coming back this far. See, and you are back to your residence. So resultant is 0. In fact, C is negative vector of A and B. C is negative vector of A plus B. This is A plus B blue colored, and C is negative of that. You know very well two vectors of equal magnitude, opposite direction are called negative of each other. In fact, I can easily write A plus B is minus C. See, A plus B is minus C. C is this, so this would be minus C. So what it becomes, in fact, A plus B plus C is going to be 0. When it comes this side, it becomes plus and you get a null vector, right? So we can state something like this. If three vectors can be represented by three sides of a triangle in order, like tail head, when you get a closed figure, obviously the result is 0. This far, this far, this far, how far from your house? 0. Clear? So if three vectors can be represented by three sides of a triangle in order, tail head, result is 0. Clear? Next, we can also add two vectors using parallelogram law of vector addition, and the statement is something like this. If two vectors can be represented by adjacent sides of a parallelogram as co-initial vectors. You know, co-initial vectors means as if they are starting from the same point. Okay, so like in case of triangle law, we were writing two vectors as two adjacent sides of a triangle in order. That means second vector should start where first vector ends, tail head, then closing side in reverse order. Okay, tail head, tail. This will be the resultant. Fine. But in parallelogram law, we are not representing two vectors as, we are not writing two vectors in order. Rather, we are writing two vectors as if they are starting from the same point, say common point O. And let this be one vector. Let me call it vector P. And let this be another vector. Let me call it vector Q. So if two vectors can be represented by adjacent sides of a parallelogram. That means you need to complete the parallelogram with these two vectors as adjacent sides. I mean vector P, let me call it vector OA as P and vector OB as Q, and we need to complete parallelogram. You know very well, parallelogram means adjacent sides, I mean opposite sides will be parallel and equal to each other magnitude wise. Let me complete the parallelogram OACB. Now this is the parallelogram OACB. Okay, OB and AC are parallel and equal, OA and BC are parallel and equal. Fine. So statement is something like this. If two vectors P and Q can be represented by two adjacent sides of a parallelogram as co-initial vectors, co-initial means as if they are starting from same point, then diagonal of this parallelogram through the common point. Mind you, you have two diagonals over here, one and this one, but don't take this one, take this one, because this is the diagonal which is passing through the common point. Common point means the point which is common to the two vectors P and Q. P and Q are starting from this common point, so we need a diagonal of this parallelogram from that common point and this diagonal. Okay, so I can say OC. This gives the resultant in both magnitude and direction. I mean this P plus Q is this, so I can safely write down this resultant as P plus Q. Fine. In fact, parallelogram law is nothing new. It can be understood with the help of triangle law. What I'll do is, I'll just translate this vector Q, I mean OB is equal to AC, so I can even call this as Q, vector Q. You know very well, vector doesn't change due to translation. We are just shifting the vector parallel to itself without changing its magnitude and direction. So instead of calling this vector as Q, I can even call this vector as Q. Now let me add this vector P and then Q using triangle law. P plus Q is something like this. See, tail, head, resultant, head, tail, which is nothing but OA plus AC is going to be OC. Tail, head, head, tail, head, tail, third side in reverse order. So it's nothing but this is R, or rather P is OA and second vector should start where first ends, that is AC. Resultant, you know, first vector's tail is tail of resultant, head of second vector, head of resultant, OC. OC is nothing but R. Fine. So P plus Q is R. Fine. Or you can even write like this. Okay. Let me write here R equal to P plus Q, and above this line let me write it Q plus P. Why I am doing this will be clear within short span of time. What I'll do is, instead of taking this vector Q and keeping it here, let the Q be here itself. Let me translate vector P now. Instead of telling OA as P, I can even call BC as P, because in a parallelogram OA and BC are equal. So this is P. Fine. I'm just translating P now, shifting it parallel to itself without changing magnitude and direction. Now what I'll do is, I'll add Q and then P. I mean instead of adding OA and then AC, let me now add OB and then BC. What happens? Let us see. OB plus BC. See, OB plus BC. Second vector should start where first vector ends. And whatever resultant, tail of first vector, tail of resultant, head of second vector, head of resultant. Once again you get OC. I mean OA plus AC is also OC. OA, AC, OC. Fine, finally result. OA plus AC, tailhead, this far. You travel this far. How far you are from your house? This far, OC. You travel this much and then this much. How far are you from your house? OC. So obviously P plus Q or Q plus P doesn't matter. Result is going to be same. Over here, what is OB? OB is Q, and what is BC? BC is P, and finally OC we know it's R. So you know P plus Q is R and Q plus P is also R. P plus Q R, Q plus P R. So what we can say is vector addition is commutative. So order of addition is not going to make much difference. It's not going to make any difference in fact. P plus Q is equal to Q plus P. Okay? Order of addition is not going to make difference. Vector addition is commutative. I have shown here only for two vectors. P plus Q is this, Q plus P is this. So P plus Q is equal to Q plus P, which is same OC. I have shown you for two vectors P and Q, but it is equally valid for any number of vectors. Even if you are going to add 100 vectors, order in which you add is not going to affect the resultant as long as you are adding the same 100 vectors. Clear? So vector addition is commutative. If two vectors can be represented as two adjacent sides of a parallelogram as co-initial vectors, then diagonal of that parallelogram, you need to complete the parallelogram with these two vectors are adjacent sides. Diagonal of the parallelogram passing through that common point, this diagonal, not this one, gives this diagonal, gives the resultant in both magnitude and direction. That means result of this P and Q is this vector. Fine. Finally, polygon law of vector addition. See, so far we have studied about triangle law and parallelogram law of vector addition. Both these laws can be used to add only two vectors. Triangle law, you know very well, when two vectors can be represented by two sides of a triangle in order, closing side of the triangle in reverse order gives resultant in both magnitude and direction. This is the vector A plus B. Fine. Resultant of these two vectors. Fine. And parallelogram law, statement of something like this. If two vectors can be represented by two adjacent sides of a parallelogram, say P and Q, then you need to complete the parallelogram first with these two vectors as adjacent sides. Then the diagonal of this parallelogram passing through the common point, this diagonal, okay, OA and OB are the two vectors. OC is the resultant. This OC is the resultant of P and Q, diagonal passing through the common point. These were the two laws of vector addition, either triangle law or parallelogram law. It doesn't matter which law you follow. Finally, result is going to be same as long as you are adding the same two vectors. Fine. But over here you see, here triangle law we are using to add only two vectors A and B. Even parallelogram law is used to add only two vectors P and Q. Fine. To get the resultant. Now let us consider something called polygon law. As the name itself is telling, polygon law. Fine. It can be used to add more than two vectors at the same time. For example, if number of vectors can be represented by adjacent sides of a polygon in order, then closing side of the polygon in reverse order gives the resultant in both magnitude and direction. For example, suppose your residence is here at point O, you are traveling to reach point capital A and displacement is small a, you are traveling from A to capital B, displacement is small b vector, and then from B to C you undergo a displacement small c vector. How far are you from your residence? It's so easy to understand. It's something like this: OA plus AB. Mind you, vector capital AB is nothing but small b, this vector, and then BC. We are writing all these vectors in order. See, tailhead, tailhead, tailhead in order. Second vector should start where first ends. Third should start where second ends. In that order when you place, definitely resultant is how far. This is the resultant. Fine. This is the resultant. This is the vector A plus B plus C. This far you are from your residence. See, you travel this much, you travel this much, travel this much. How far are you from your residence? This far, this far. Tailhead, 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 head, tail. Okay. So this is nothing but OC. That means tail of the first vector, tail of the resultant, head of the last vector, head of the resultant. Second vector should start where first vector ends. Third vector should start where second vector ends. OA, AB, BC. You can have as many as you wish. Result will be OC, like AB, OA, AB, BC, CD, DE. Result will be OE. Something like tailhead, 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 tailhead. Resultant head, tail. Closing side in reverse order. Fine. So tailhead, tailhead, tailhead. Resultant head, tail. Closing side of this polygon. Tailhead, 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 head, tail. Closing side in reverse order is resultant in both magnitude and direction. Resultant of all these vectors. Fine. So this is polygon law of vector addition. In fact, even polygon law can be considered as repetitive application of triangle law. What I'll do is, let me just add vectors A and B using triangle law first. Just I'm adding A and B using triangle law. Tail, head, resultant will be head tail, this closing side. This will be the resultant of A and B using triangle law. See, tail head, head tail, tail head tail. Instead of taking A and B, I can take the resultant A plus B. Tail head tail. Now to this vector A plus B. Remember, A plus B is now single vector. The effect of these two vectors is, effect of this and this vector is this single vector A plus B. I mean OA plus AB will be OB. Now to this A plus B, let me add the vector C. Fine. Now what I am doing is, I am adding vector A plus B to vector C. Tail head, resultant head tail, tail head, resultant head tail. Fine. So this is the resultant. What I am doing is nothing but I am applying triangle law twice. If you need to add more than 3 vectors, you may need to apply triangle law repeatedly. So polygon law can be understood as if nothing but it is the repetitive application of triangle law. See, tail head tail. Then again tail head tail. Fine. To this A plus B you are adding C to get this resultant. Fine. Something like this. One more thing you can understand with the help of this polygon law is vector addition is associative. For example, now I am adding A and B first to get A plus B. Then I am adding C to this A plus B. I am adding C. I get this. Fine. So A plus B plus C. A plus B plus C is this OC. Fine. What I will do is, now what will I do is, instead of adding A and B, let me add first B and C. See, B is the vector AB and C is the vector BC. So let me add these two vectors B and C. Tail head. Resultant will be head tail, reverse order, closing side in reverse order. See, tail head, resultant head tail, triangle law. So this red colored vector is B plus C. See, tail head, resultant head tail. This is B plus C, AC. Fine. Now to this B plus C, let me add vector A now. This B plus C and A. See, tail head, resultant head tail. Same thing I am getting. Fine. I mean A plus B plus C. How far are you? This far. OC. A plus B plus C. OC. A plus B plus C. Same OC. A plus B plus C is OC. Fine. So what I can say is, now you can either write A plus B, you can either add A and B first and then C, or you can add B plus C first to get their resultant and then to their resultant you can add A. Resultant is one and the same. Fine. So vector addition is associative, which is clearly shown with the help of this polygon law. Remember, first I am adding this A and B using triangle law. Tail head tail. This blue colored OB is the vector A plus B. To this vector let me add C. Tail head tail, OC. Tail head tail. This is the resultant vector. Fine. Tail head tail. A plus B plus C is OC only. Fine. Now let me add B and C first. This B and C first. Okay. So B plus C. Tail head, resultant head tail. So this is the vector. Capital AC is the vector B plus C. To this B plus C, let me add A. Tail head tail. Same thing. A plus B plus C. Once again OC. A plus B plus C is OC. A plus B plus C is also OC. That means A plus B plus C is equal to A plus B plus C. Vector addition is associative, which can easily be shown with the help of polygon law. Polygon law can be used to add any number of vectors at the same time. Fine. Let's now discuss about subtraction of vectors. Suppose this is vector A and this is vector B, and I need to subtract vector B from vector A. That means I need A minus B. In fact, there is no separate law for subtraction of vectors. Subtraction of one vector from another vector is done by the laws of vector addition only. Okay, so what we do is we write A minus B as A plus of minus b. What is minus b? This is negative vector of vector b. So now what we do is we take minus b and then add it to vector a. This is vector b, so this is going to be minus b. A vector whose magnitude is equal to that of b but direction is opposite to that of b. This becomes minus b. Okay, now this minus b, I need to add it to vector a. So when you add minus b to vector a, you get a minus b, because plus of minus is minus, fine. So a minus b is same as a plus of minus b. The vector which is to be subtracted, over here vector b is to be subtracted from vector a. We take negative of that vector. We take negative vector of vector b and add it to a. The vector which is to be subtracted is negated. It's made negative and then it is added to this vector a. Okay, right now I need a minus b, so I need to subtract b. So let me take the vector which is to be subtracted is b. I need to take negative vector of b, the vector which is to be subtracted. We take negative of that vector and add it to vector a. So a minus b is going to be a plus minus b. So this minus b, I need to add it to a. This minus b is this vector, tail head, resultant head tail. This is the vector a minus b. Okay, a plus of minus b or a minus b, this single vector. If I call this as o, a, some point b and this point some c. So oa plus ac, mind you ac is not b, it is minus b, fine. So tail head, resultant head tail, triangle law. But the vector which is to be subtracted b, this is the vector b. In fact ab is vector b, this vector is to be subtracted. So I need a minus of this is nothing but this. So tail head is head tail. So the vector which is to be subtracted from vector a is negated and then added to a, fine. Now suppose you need a Now what if you need b minus a? Obviously the same thing. But now we need to subtract vector a, so we need to negate vector a and then add it to b, fine. This is vector a, small a, oa is vector a. I don't need a right now, I need minus a, negative vector of this vector, same magnitude as that of a, same length but opposite direction, fine. So this OA is small a vector. I need another vector of same magnitude, same length but opposite direction. Let me call this vector as minus a. Okay, this is vector a, this is vector minus a, and that minus a now I need to add it to b. So I will get b minus a, the vector which is to be subtracted, we take its negative vector and add it to b. So tail head, I need to add it to this b. Tail head, resultant head tail, triangle law, fine. So this is the resultant b minus a. In fact resultant of b and minus a means b minus a, fine. This is a minus b, this is b minus a, fine. A and b, this is vector a, this is vector b. A minus b, tail head, head tail. So this becomes a minus b. This is a, this is minus a. If I need b minus a, it will be nothing but b plus of minus a. So this is a, this is minus a. This minus a, I need to add it to b. Tail head, resultant head tail. So this is b minus a, fine. If you want a plus b, what is that? You know very well. That's nothing but this is a, this is b. So tail head, resultant head tail. This is the resultant of a and b. Okay, and this is a minus b, fine. This b is negative vector minus b. I need minus b, I need to add it to a. Tail head tail. This is a minus b, this is b minus a, this is a plus b. Tail head head tail, a plus b, fine. Is it clear? So subtraction, no separate law, is done by laws of vector addition only. If you need to subtract a given vector, say b from vector a, if you need to subtract a given vector b from vector a, we take negative vector of b and then add it to vector a. We take negative vector of b and add it to a. This is how subtraction is done. Clear? Let us now consider multiplication of a vector by scalar. Suppose this is vector A. If we multiply this vector by some scalar n, what do you get? We can show easily you get another vector B, and in fact this both vectors n we will have same direction if n is positive scalar, and this a and b will have opposite direction if n is a negative scalar. But one thing is pretty sure, when a vector A is multiplied by some scalar n, you get another vector B such that A and B will be in same direction if n is positive, A and B will be in opposite direction if n is negative. It's so easy to show you. For example, I am exerting a force of 3 Newton here. Vector A is 3 Newton towards east. According to this convention, eastwards. I am pushing with a 3 Newton force to this wall. What if I multiply this force by 10? 10 just a number, a scalar. If I multiply this by 10, what you get? Obviously you get force only, another force 10 times more than this force. So it's going to be 10 times 3 Newton is going to be 10 into 3 Newton is going to be 30 Newton. Once again it is going to be in eastward direction only, because I am multiplying by a positive scalar. In this case I am taken as A as 3 Newton towards east, and I have taken as 10, I am multiplying by scalar 10, positive scalar, so I get another vector, a big vector, but in the same direction. Okay, so I get another vector B which is n times A, 10 times this, but you get, okay, both are in the same direction because in this case scalar was positive. Mind you, if this scalar is going to be negative, then they are going to be in opposite direction. For example, if I multiply this vector by minus 10, then B will not be 30 Newton, it will be minus 30 Newton towards east. But minus east is nothing but west. East minus east. If you take this direction positive, then you know very well minus east is nothing but opposite direction. So minus east can be written as opposite to east. So this can be written as 30 Newton west. Fine. Remember here A is 3 Newton east, and I am multiplying this by minus 10. So minus 10 into this becomes minus 30 Newton east. Okay, minus east is west. So B becomes 13 Newton towards west. So you get another vector, but it is in opposite direction, this side. Okay, not towards east but towards west. So when a vector is multiplied by scalar, you get another vector. Both vectors will be in same direction, provided n is positive. They will be in opposite direction if n is negative. Fine. Is it clear? I'll give you a simple example over here. One more beautiful example which most of you might be knowing it. In fact, you will be knowing it. Simple equation. When you multiply acceleration with mass, you get force F equal to ma. And you all know very well mass is always positive scalar. So these two vectors are always going to be in same direction. So acceleration of any particle will be always in the direction of net external force acting on it. Over here there is an external force which is mass of the particle into acceleration of that particle. Fine. So when a vector A is multiplied by a scalar, you get another vector. Both vectors will be in same direction if scalar is positive. Fine. And they will be in opposite direction if scalar is negative. Over here mass being positive, these two vectors will be in same direction. Mind you, these two vectors need not have same unit. For example, A and B need not have same unit. In this case, you know, acceleration is measured in meter per second square, whereas force is measured in newtons. You know, 1 Newton is nothing but mass is 1 kilogram. It's a unit of mass. And acceleration is 1 meter per second square. This 1 kilogram into 1 meter per second square is 1 Newton. We'll see later. And acceleration's unit is just meter per second square, whereas unit of force is the whole thing, kilogram meter per second square. So that is Newton. So A and B need not have the same unit. They may have the same unit, may not have the same unit. But one thing is for sure, if n is positive, A and B will be in same direction. If n is negative, A and B will be in opposite direction. That means when a vector is multiplied by scalar, we get another vector. Both vectors will be in same direction if n is positive, and if n is negative, A and B will be in opposite direction. And if this n is just number without any unit, n is not having a unit, just like say 3 or just like say 10, then 10 into 3 Newton towards east, I'll get another vector which unit will be same. That means if n is not having a unit, a and b will have same unit. But if n is having a unit, then a and b will have a different unit. Over here mass is having a unit, therefore force and acceleration, two vectors will have a different unit. Fine? So if this scalar is having a unit of its own, then vectors a and b will have different units. If the scalar is not having any unit, just number, then a and b will have same unit. Is that clear? So this finishes multiplication of a vector by scalar. Let us now consider division of a vector by scalar. It is just as simple as multiplication of a vector by scalar. For example, a is a vector, and if you divide this vector by scalar n, what do you get? See, remember, a by n can as well be written like this: 1 by n into a. Fine? So when n is scalar, definitely 1 by n is going to be scalar. For example, just 5 is scalar, so 1 by 5 also will be a scalar. Just, okay, it doesn't get some direction from somewhere. It doesn't get direction from anywhere. Fine. So a by n, vector a divided by scalar n, can be written as 1 by n into a. But 1 by n is some another scalar, suppose say m into a. Remember, for 1 by n I am writing it as some m. Here m need not be mass, but some scalar 1 by n as m. So what I am trying to tell you is, dividing a vector by scalar n is same as multiplying the vector by scalar 1 by n. Multiplying a vector by scalar 1 by n is nothing but some scalar. Multiplying by scalar means you get another vector. You get another vector c, suppose, and these two vectors will be in same direction. If this scalar is positive, n is positive, means m will be positive. Is it clear? N is positive means 1 by n will be positive. And if n is negative, 1 by n will be negative, m will be negative. M is nothing but 1 by n. For this thing I am writing m. And when this is negative scalar, a and c will be in opposite direction. Is it clear? So dividing a vector by scalar n is same as multiplying the vector a by another scalar 1 by n. Obviously, multiplying a vector by scalar, you know very well you get another vector only, and these two vectors will be in same direction provided this scalar is positive, and if this scalar is negative, a and c will be in opposite direction. Moreover, this a and c need not have same unit. If this scalar is not having a unit, then a and c will have same unit. If this scalar is having a unit, then a and c will have different units. Dividing a vector by scalar is same as multiplying a vector by another scalar. Multiplying a vector by scalar means like a into n only, fine? But another scalar. But still you end up getting a vector. Both vectors will be in same direction. If n is positive, they will be in opposite direction. If n is negative, a and c will have same unit. If n is not having a unit, a and c will have different unit. If n is having a unit. Is that clear? With that we have completed multiplication of a vector by scalar, division of a vector by scalar. In both cases you end up getting a vector. Fine. Lot more is there, multiplication of a vector with another vector and applications, but that you are going to learn in your higher classes. As of my goal was not to teach you vectors and scalars in detail, but the goal was to make you understand basic idea about vectors and scalars so that you can understand very clearly the next few chapters, that is kinematics, laws of motion and other, where you encounter some physical quantities like velocity, acceleration, momentum, force. They are vector quantities, and if you don't know these ideas, how vectors get added up and how to subtract one vector from another vector, what happens when you multiply a vector like acceleration by another scalar mass, obviously you need to know these basic things, only then you can understand those chapters clearly. Fine. And the goal is to make you understand those topics, not just by hearting without understanding. The goal is to understand. Fine. So that's the reason I have given a brief introduction to vectors and scalars. More about vectors and scalars you are going to learn in much detail in both physics and mathematics in your higher classes. Fine.